Hello, my name is Jonah Treitler, and the title of my presentation is Evaluating and Reducing AI Model Group Disparity, an Analysis on COVID Test Outcomes in Children. This study aims to shed light on the critical intersections of artificial intelligence and healthcare, specifically focusing on the disparities that may arise regarding COVID test outcomes in children. Now, an introduction. AI fairness is a topic of increasing significance in the healthcare landscape. With the rising prevalence of AI modeling, many problems arise, including the concern that biased models may perpetuate or exacerbate existing health disparities. To navigate this complex landscape, we will investigate the metrics that evaluate fairness, including parity, accuracy, and true positive and false positive rates. Moreover, our exploration will touch upon a strategy to mitigate AI health disparity using the generation and incorporation of synthetic data. So now let's talk about specific instances of group disparity identified in prior studies. Well, for example, a study that applied a machine learning algorithm to unstructured clinical and psychiatric notes unraveled disparities in predicting ICU, intensive care unit, mortality, and 30-day psychiatric readmission. This work unveils differences in prediction accuracy and machine bias concerning race, gender, and insurance payer types. To provide a visual understanding, there are three graphs on the right that encapsulate the disparities that were addressed in this study. So, some background. Turning our attention to the specific challenges that COVID poses in children, we acknowledge its profound impact on millions of young lives globally. Children, like adults, may encounter disparities based on demographics such as race and ethnicity. While most are resilient, a subset of underlying conditions are particularly vulnerable to severe outcomes. Some researchers have turned to machine learning algorithms, showing their capabilities to analyze pediatric COVID 19 data, but today we will aim to unravel potential disparities in this domain, recognizing the unique considerations and implications for children. So, the two research questions for this study are: what is the prevalence and magnitude of group disparity when modeling COVID test outcomes in children? And can the generation of synthetic training data reduce group disparity on smaller populations? So, below is a list of key acronyms that we will go over during our study, and you can take a moment to read these. Also, a quick reminder is that group parity, a definition for group parity, is the performance of a given AI model on a disadvantaged subgroup that is comparable to that on another subgroup or the general population. So let's move forward. Let's look at the data set. So, our data set, we obtained a set of National Health Interview Survey, NHIS, data from 2020 to 2022 from the IPUMS 12, which is a national survey, and we identified a cohort of children ages 0 to 17. Note that NHIS is a nationally representative sample. For the ML experiments, COVID test result, positive or negative, was used as the outcome variable, and in pre-processing, features with high amounts of missing values were eliminated, leaving us with a set of 16 variables, which is 32 after one hot encoding, which is essentially just a way of making categories into binary variables. So let's focus on the specifics of our study cohort. So in summary, our cohort comprised of 9,935 individuals with a mean age of 9.13 and a standard deviation of 5.29. Regarding gender, 48.2% are female and 51% are male. The racial breakdown includes the majority being white, with 12% being black, 7% being Asian, and 6.5% being mixed race, as well as Alaska Natives and Native Americans taking up 2.5%. Ethnicity distribution encompasses non-Hispanic / Spanish origin, which is 80.8%, and Mexican, 11.5%, and other Hispanic, 7.6%. Other characteristics, such as U.S. citizenship, receipt of food stamps, insurance coverage, and health status, provide a comprehensive overview of our cohort. And at the bottom, you can see the amount of positive COVID test results from our data set. So we selected 12 small subgroups, including 6 racial and ethnic minorities. We employed 5 different algorithms, including a gradient boosting machine, neural network, penalized logistic regression, support vector machine with a linear kernel, and k-nearest neighbor, and then assessed group parity for each of these. So our data was partitioned into 90% training and 10% testing, with a model fitting and parameter selection employing a 5-fold cross-validation approach. We then calculated the AUCs and compared for the overall population and each subgroup in the testing data, with training and testing repeated 10 times per algorithm. Then paired t-tests assess the statistical significance of group disparities between subgroups and the overall population. And on the right, you can see a flowchart that accompanies this process. So now let's explore our approach to mitigating these group disparities using synthetic data. So subgroups with AUCs significantly lower than the general population were identified, and we used 2 different methods, oversampling and generative adversarial network, or GAN. And we used these to generate synthetic data, nearly doubling the sample size of selected subgroups in the training data. This experiment, repeated 10 times with different random splits, evaluated neural network models both with and without synthetic data, as well as the other machine learning methods. Statistical comparisons were made to understand the impact of the synthetic data on reducing group disparity, and on the right you can see a revised flowchart that goes through our methods for this part. Lastly, this is just a visual depiction of how a generative adversarial network works, and it shows how this method is quite unique and innovative, and how it aided us in synthetic generation of data. In our group parity assessment, we compared the AUCs of 50 models, 5 algorithms with 10 different data partitions each, in the 12 small subgroups with those in the general population. Our results showed that 50.7% of the time, the AUCs of a small subgroup were lower than that of the general population, underscoring the prevalence of group disparity. However, despite this prevalence, there exists a significant variation in AUC differences, the mean being 0.01, the minimum being negative 0.29, the maximum being 0.41, and the standard deviation being 0.09, where a positive difference indicates AUC disparity. This detailed information is also shown below on a graph that outlines each machine learning method, the mean AUC on the general population, and the AUC disparity with standard deviations included. Further analysis through the paired t-tests revealed statistically significant lower AUCs in 4 subgroups. The table in this slide elucidates the specifics, showing the 4 subgroups, including their respective AUCs with standard deviation, the AUC differences, and the p-values. It is essential to note that the vast majority of children in the NHIS survey reported excellent or very good health, and so reporting good health represents a small subset that is less favorable, that has a less favorable health status than the majority of children. Turning our attention to mitigating disparity, we focused on models that exhibited disparity and employed oversampling and GAN techniques. Encouragingly, 50.7% of the time, our oversampling and GAN did reduce AUC disparity when using these synthetic data methods. Furthermore, in cases where AUC disparity was reduced, GAN exhibited a decrease from an average of 0.08 to 0.03, while oversampling reduced it from 0.08 to 0.05, meaning less disparity. For a visual representation, here are the two graphs. One of them showcases the percent of ML models with reduced AUC disparity, and the other illustrates the average reduction in AUC disparity. Our discussion begins with the recognition that across 5 distinct machine learning algorithms, prediction disparity is prevalent in modeling COVID outcomes in children. It is important to acknowledge that most of this disparity may be attributed to random effects associated with data partitioning and the use of random seeds in algorithms. Additionally, certain subgroups demonstrated statistically significantly worse AUCs than the general population, as revealed by the paired t-test results. Continuing our discussion, we explore the impact of adding synthetic data from oversampling and GAN for selected subpopulations. While these interventions reduced prediction disparity in some cases, it's crucial to note that GAN, in particular, requires substantial data for training, which can be challenging for small subgroups. Future studies may explore alternative bias mitigation methods on larger samples, addressing the complexities associated with multi-minority status. Finally, we would like to express our gratitude and acknowledge those who have played a crucial role in our research. So we would like to thank the Aim Ahead pilot program for their support, and we would also like to thank the CDC and IPUMS that made the NHIS data freely and publicly available, as well as the ML packages from R, including GAN, which have been instrumental in our research endeavors. Thank you.